Good evening, student. Welcome to our fifth lecture on circuit theory. Today we will learn about the Laplace transform. The Laplace transform we have dealt with so far the time function. Now we will obtain another function of s from ft, and this is the Laplace transform operator. Laplace transform of ft is equal to fs, and Laplace transform of ft is defined as integration minus infinity to plus infinity ft e to the power minus st dt. Now, as we are concerned about only the causal signal, now the signal ft is a causal signal. So, ft is equal to 0 when t less than 0. So, the integration will be reduced to 0 to infinity ft e to the power minus st dt. So from a time function we will go to a space function of s. Now the utility of Laplace transform is the differential equation. One differential equation can be easily solved by a Laplace transform analysis. Now differential equation will be converted to an algebraic one. Algebraic equation. Now we all know that the algebraic equation is easier to solve than the differential equation. Now once the equation is solved, we will go to the time function again from the Laplace transform, inverse Laplace transform. So inverse Laplace transform of fs will give us the time function. Now the inverse Laplace transform of fs is defined as 1 by 2 pi j c plus j infinity, sorry, this is c minus j infinity to c plus j infinity fs e to the power st dt, where c is a real constant. Now the detail of the mathematics are not needed. We will not discuss about the detailed mathematics in every time. Now we will discuss about the exponential function first, e to the power minus st or e to the power st. Exponential function is e to the power st. The exponential function is e to the power st. Now from the Maclaurin series we know that e to the power st is equal to 1 plus st plus a square t square by factorial 2 plus s cube t cube by factorial 3 plus so on. Now as e to the power st is a quantity, so it must have one particular dimension. So this dimension should be equal to the dimension of 1 plus dimension of e to the power st plus dimension of this quantity and so on. So e to the power st will have a particular dimension if and only if the dimension of S is equal to the dimension of T, 1 by the dimension of T, because only in this case e to the power st will be a dimensionless quantity, okay, or dimension will be equal to 0. So the dimension of S equal to 1 by the dimension of T. So S is a frequency. Okay, generally we call it a complex frequency. Therefore, we can express it as S equal to sigma plus j omega. Sigma means the real part of S and we call it the Nepar frequency, and the unit of sigma is Nepar per second, and omega we call it the radian frequency. And the unit of omega is radian per second. Now, if S is a real quantity, that is, if omega equal to 0, then S equal to only sigma. So e to the power st is equal to e to the power sigma t. Now e to the power, the graph of e to the power sigma t will look like this one. This is or the graph of e to the power sigma t, is equal to this one when sigma is equal to 0, or if sigma is equal to 0, e to the power sigma t equal to 1 always. So this is the graph of e to the power sigma t when sigma equal to 0. If sigma less than 0, then the graph looks like this one. This is a exponentially decreasing quantity. When t equal to 0, e to the power sigma t is equal to 1, and this is the case when sigma greater than 0, or the graph will be a exponentially increasing quantity. Okay, now if case 2, this is case 1, if sigma is a real quantity. Now case 2, we will consider if S is an imaginary quantity, or sigma equal to 0. If sigma equal to 0, S equal to j omega only. So e to the power st is what? E to the power st equal to e to the power j omega t. So the graph of e to the power j omega t is a circle of radius 1. E to the power j omega t is equal to 1 into e to the power j omega t. So e to the power j omega t is a circle of radius 1, and the graph and the phasor, this phasor 1 is rotating at a speed of omega radian per second counterclockwise. So this is the real axis and this is the imaginary axis. The real axis the real part of e to the power st here is this one. Okay, when t equal to 0, the real part is equal to 1. When t equal to 0, the real part is 1, and the projection on real axis of this phasor will decrease, and at this point the projection is equal to 0. This projection will get 0 here, and when the phasor will rotate further, the projection on x-axis or real axis will be negative. Here this is negative. The negative projection will increase and will attain the maximum value here. The negative projection will increase and attain the maximum value. And when the phasor rotates further, the projection on real axis will get decrease again, and this will get 0 again. Okay, and the imaginary, this is the real part of e to the power st, and imaginary part of e to the power st will look like this one. This is the imaginary part of e to the power st. And we all know from the Euler's equation that e to the power j omega t is equal to what? Cos omega t plus j sin omega t. So the real part of e to the power st will be cos 1, will be cos omega t, and the imaginary part will be sin omega t. Okay. Now we will consider, in next case or case 3, we will consider S as an complex quantity. Now in case 3, we will consider S as a complex quantity, that is S equal to sigma plus j omega. Now sigma is not equal to 0 and j omega not equal to 0. So e to the power st is equal to what? E to the power sigma t into e to the power j omega t. So the graph of e to the power st will be like this one. This will increase further and further. If sigma is equal to sigma greater than 0 or sigma is positive, then this will increase further and further, and the real part of this one will be the real part of e to the power st will be this one. This one is the graph of e to the power sigma t into cos omega t. Therefore, this value will get increase as the time increases, and the imaginary part will also get increased in this fashion. Okay, and this is the equation of imaginary part of e to the power st, and this is the equation of e to the power sigma t, e to the power sigma t into sin omega t. Okay, now this is, say, case 3a. Now case 3b, in case 3b, we will consider S as the complex quantity e to the power st equal to e to the power sigma t into e to the power j omega t, but in but here we will consider the case when sigma is negative or sigma less than 0. Now e to the power st will take this form. The form of an Archimedean spiral. The form of an Archimedean spiral. This is the graph of e to the power st with sigma less than 0. So the real part of this one, real part of e to the power st will be this one. This is a damped cosine. The magnitude will get decreased with time, and the equation of the real part is e to the power sigma t cos omega t with sigma less than 0, and the graph of the imaginary part will be a damped sinusoid. Imaginary part of e to the power st is what? A damped sinusoid, or the magnitude of the sinusoid will get decreased with time, and this is the equation of e to the power sigma t sin omega t with sigma less than 0. Okay, now as S is complex, or as S is sigma plus j omega, so we can call this plane as S plane, where this is the real axis, this is the real axis or the axis of sigma, and this is the imaginary axis or the axis of omega. So this is the right hand plane, this is the right hand plane, and this is the left hand plane. This is the upper part of right hand plane, U R H P, and this is the lower part of right hand plane. This is also the upper part of left half plane or left hand plane, and this is the lower part of left hand plane. Okay, this is very important in control system analysis. Now let us go to the Laplace transform directly. Now let us discuss about the Laplace transform directly. Now the Laplace transform of the time function ft is given by fs. The capital letter, we will use the capital letter F here, and the Laplace transform of ft is defined as, this is an integration 0 to infinity ft e to the power minus st dt. Okay, and we will call the Laplace transform of gt is equal to g of s. This is capital letter G, and this is the function of a complex frequency S. Okay, now we will discuss about some basic or important properties of Laplace transform. Now the properties of Laplace transform. Now the important properties of Laplace transform, first comes this one. If the Laplace transform of ft is equal to fs and Laplace transform of gt is gs, then the Laplace transform of aft plus bgt is what? This is equal to AFS plus BGS, or this follows the linearity property. Now, property 2 tells us that if Laplace transform of ft is equal to Fs, okay, if Laplace transform of ft is equal to Fs, then ft and Fs, these are Laplace transform pair. If the Laplace transform of ft is equal to Fs, or inverse Laplace transform of Fs is equal to ft, then ft and Fs are called Laplace transform pairs. Okay. Now, if Laplace transform of ft is equal to Fs, then Laplace transform of aft, this is the product of a and ft, this is equal to a into Fs. Okay. Now property 3 tells us that if ft and Fs are Laplace transform pairs, that is, if Laplace transform of ft is equal to Fs, then the Laplace transform of the derivative of ft, or ddt of ft, is equal to sFs minus f0. Similarly, the Laplace transform of the second derivative of ft is what? This is s square Fs minus sf0 minus f dash 0, and so on. Okay. Now, if all the initial conditions are 0, then with all the initial conditions equal to 0, that is, if ft equal to f0 equal to 0, f dash 0 equal to 0, and so on, then the Laplace transform of ddt of ft will be sFs, and the Laplace transform of d square dt square ft equal to what? S square Fs. And in general, the Laplace transform of this one equal to what? S to the power n Fs. Okay. Now, the basic property 4 tells us that if ft and Fs are Laplace transform pairs, that is, if Laplace transform of ft is equal to Fs, then the Laplace transform of integration 0 to t ft dt equal to what? Fs by s, with all initial conditions equal to 0. Okay. There are few more properties. We will discuss about them in due time. Now, let us determine the Laplace transform of the basic functions. Now, say we want to determine the Laplace transform of e to the power at, or if ft equal to e to the power at, then we want to determine the fs. So the Laplace transform of e to the power at is what? E to the power at equal to 0 to infinity e to the power at e to the power minus st dt, or this is what? This is 0 to infinity e to the power minus s minus a t dt. This will give us 1 by s minus a minus of 1 by s minus a e to the power minus s minus a t 0 to infinity. So e to the power minus infinity minus e to the power 0. This is minus of e to the power minus of 1 by s minus a e to the power minus infinity minus e to the power 0. So what is the value of e to the power minus infinity? E to the power minus infinity equal to 1 by e to the power infinity, or this is 1 by infinity, or this is equal to 0. So and e to the power 0 equal to, we know that e to the power 0 is 1. So the Laplace transform of e to the power at is 1 by s minus a. Similarly, Laplace transform of e to the power minus at is what? E to the power minus at is 1 by s plus a. Okay. Now let us determine the Laplace transform of unit step function. Laplace transform of unit step function. Now, what is the unit step function? Unit step function, the value of unit step function is equal to 1 when t greater than equal to 0, and this is equal to 0 when t less than 0, or this is the graph of unit step function ut. Okay. Now Laplace transform of ut is equal to 0 to infinity ut e to the power minus st dt. Now at this interval ut is equal to 1, so this is e to the power minus st dt. So the integration gives us e to the power minus s minus of 1 by s e to the power minus st 0 to infinity. So this gives us minus 1 by s 0 minus 1. So or this is equal to 1 by s. Okay. Now let us determine the Laplace transform of sin omega t and cos omega t. Now let us determine the Laplace transform of sin omega t and Laplace transform of cos omega t simultaneously. We will determine these two Laplace transforms simultaneously. Now from the Euler's equation we know that e to the power j omega t equal to what? Cos omega t plus j sin omega t, and e to the power minus j omega t is equal to what? Cos omega t minus j sin omega t. Therefore, let us add these two quantities. So, e to the power j omega t plus e to the power minus j omega t equal to what? 2 cos omega t. So, cos omega t is equal to half e to the power j omega t plus e to the power minus j omega t. Okay, now let us subtract this quantity from this one. So e to the power j omega t minus e to the power minus j omega t gives us 2j sin omega t. Therefore sin omega t is 1 by 2j e to the power j omega t minus e to the power minus j omega t. And we know that the Laplace transform of e to the power j omega t equal to what? 1 by s minus j omega, and the Laplace transform of e to the power minus j omega t is what? 1 by s plus j omega. So the Laplace transform of cos omega t is what? Half into the Laplace transform of Laplace transform of e to the power j omega t plus Laplace transform of e to the power minus j omega t. Okay, so Laplace transform of cos omega t is half of 1 by s minus j omega plus 1 by s plus j omega. So this gives us half into s square minus j square omega square. This is s plus, at the numerator, s plus j omega plus s minus j omega. Now plus j omega and minus j omega will be cancelled out. So half into 2s, and we know that j square equal to minus 1. So at the denominator we get s square plus omega square. So half and 2 will cancel out. So Laplace transform of cos omega t is equal to s by s square plus omega square. Okay, and Laplace transform of sin omega t will be 1 by 2j Laplace transform of e to the power j omega t minus e to the power minus j omega t. Okay, this is equal to 1 by 2j 1 by s minus j omega minus this is 1 by s plus j omega. This is what? This is equal to s square minus j square omega square, and in the numerator we will get s plus j omega minus s plus j omega. So we know that j square equal to minus 1, so this is equal to 1 by 2j into 2j omega by s square plus omega square. So 2j and 2j will cancel out each other. So the Laplace transform of sin omega t is equal to what? This is equal to omega by s square plus omega square. Okay, now let us determine the Laplace transform of cos hyperbolic bt and sin hyperbolic bt simultaneously. and we know that cos hyperbolic bt is equal to half into e to the power bt plus e to the power minus bt, and sin hyperbolic bt is equal to half of e to the power bt minus e to the power minus bt. Okay, therefore Laplace transform of cos hyperbolic bt is equal to half into Laplace transform of e to the power bt, that is s minus b, plus Laplace transform of e to the power minus bt, that is 1 by s plus b. So this is equal to half into s square minus b square s plus b plus s minus b. So plus b and minus b will cancel out. So this is equal to s by s square minus b square, and Laplace transform of sin hyperbolic bt is equal to half of Laplace transform of e to the power bt is equal to 1 by s minus b, and Laplace transform of minus Laplace transform of e to the power minus bt is 1 by s plus b. So this is equal to half into, in the denominator the quantity is s square minus b square, and in the numerator the quantity is s plus b minus s plus b. Plus s and minus s will cancel out. So this is equal to b by s square minus b square. So as we are pushing the time, so let us call it a day. We will continue further next day. Thank you.